Okay, you did a success criteria. So, Carly H., what'd you write? You don't know what you wrote? Oh, so you just ignored what we were supposed to do. Okay. Stephen, what'd you write?
Being able to tell what types of bonds, polyatomic,
Ion. Okay. Polyatomic ions we're going to talk about a little bit here. And with diatomic and polyatomic, let's just start by breaking them down. What's diatomic? Okay. Two atoms. So then poly would be more than two or more atoms. So we're going to talk about those polyatomic and diatomics. And remember, okay, remember what a molecule is. What's a molecule mean to us? What does a molecule mean, Paige? That it's covalently bonded. Excellent. So those covalently bonded molecules, these diatomic molecules, covalently bonded, we could have polyatomic molecules, as we'll see here in a second, but we also have polyatomic ions. And as Stephen said, it's going to be some unique bonding for us because we're going to see that the polyatomic ions will be covalently bonded together, but then they will ionically bond with something else. So they will have both types of bonding, okay? So that was the polyatomics. Kira, what did you write? The super seven, the diatomics are very important. We're going to go over these throughout the rest of the year. They do not appear by themselves. They are always diatomic. Okay? So when we talk about the super seven, we need to know that they are two, like H2, O2. And we'll see that a lot. Where this comes into play a lot is when we are doing our reaction predictions, okay? And we need to know if something's reacting with oxygen, it's O2. So the learning target here we have for this particular lesson is, once again, to describe characteristics of covalent bonding. Now, the success criteria, what we need to do to be able to hit this learning target today is to identify the diatomic elements, the super seven. We also need to be able to describe a polyatomic ion. So we hit both of those success criteria when you folks were writing things down. So let's begin by diatomic elements. We said di is two, so these are elements that are two atoms, okay? The super seven, as I refer to them, and many, I'm sure, many chemistry teachers refer to the super seven, okay? Here is a diagram that I thought was really, really good because it helps us understand why they are the super seven. A few things. Number one, they start with element number 7 here, nitrogen. On the periodic table, when I highlighted these, you can see that they make a 7 other than hydrogen all the way over here by himself. Okay, so these make a 7. Boom, boom. And also, there are 1, 2, 3, 4, 5, 6, and hydrogen 7. So they start with the number 7, they make a number 7, and there are 7 of them. That is why we refer to these as the super 7. So we have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine down on the bottom. If we look at nitrogen, right here are nitrogen gas molecules bouncing around in this little box. Now, nitrogen is element number 7. So how many valence electrons does nitrogen have? Stephen? 5 valence electrons, good. 7 total, 5 valence. So how many open bonding sites does nitrogen have? 3 open bonding sites. So when nitrogen bonds with itself, what's some things you can tell me as far as the bonding? Okay, what's one thing you think you could tell me when nitrogen bonds with itself? Tyler? It's a covalent bond. Okay, what type of a covalent bond? Okay, remember we have 2 different types of covalent bonds. A nonpolar covalent bond, good, because electronegativities, they're both nitrogen, right? So what should the difference be? 0, okay? So it's a nonpolar covalent bond, and in terms of how many electrons being shared, would you say it would be a double, a single, double, or a triple nonpolar covalent bond? A triple, good. Because each nitrogen has 3 open bonding sites, correct? So in order to obey the octet rule, we're going to see that that's going to be a triple nonpolar covalent bond. So that's pretty descriptive right there, okay? Pretty descriptive. So when we see this nitrogen, all right, when we see this nitrogen, we know anytime that we have nitrogen, it is going to be diatomic with the subscript 2, because there's going to be 2 of them. So if I'm writing this out for nitrogen right here, it would be N2. Now, just some facts about nitrogen to review with you. I'm sure one time or another you've probably heard this. But the air that we are breathing in right now, okay, is a lot nitrogen. Anybody know how much nitrogen's in the air? Tyler, what do you think? Little bit higher. Yeah, you're in the right ballpark. 78%. 78% of the air that we are breathing in is nitrogen. 21% of the air we are breathing in is oxygen. So 78 and 21 gives me 99. So we're pretty close to 100 there. There's some trace amounts of other things in the air we breathe. I'm sure there got to be some carbon dioxide, right? Because that's what we're exhaling. So now, these are diatomics, nitrogen is. I'm going to show you here a monoatomic. Right here is argon. If we look at argon, okay, argon right here, it is in red. So argon is, once again, a gas. It is a noble gas. Noble gases have filled outermost energy levels. Their shells are filled. So argon is not diatomic. It's just bouncing around different argons by itself. Now here's another box of oxygen. All right, let's talk a little bit and see what we know about oxygen. Aiden, how many valence electrons would oxygen have? 6 valence electrons, good. So how many open bonding sites, Madison? 2, good. So it has 2 sites open. So what do we predict? Okay, a single, double, or triple bond? A double, right? Because each oxygen has 2 open bonding sites. So we would think, and it's going to happen, that this oxygen and this oxygen, they are going to double bond together to obey the octet rule. So oxygen, we're going to see, never is by itself. It's going to be diatomic, O2. Here's a slide that I put up here that down here on the bottom has the super 7, and as we would write them out, hydrogen H2, oxygen O2, bromine Br2, fluorine F2, iodine I2, nitrogen N2, chlorine Cl2. So those are the super 7, and I've included some atomic radii. Now over here shows you, and I don't know when we discussed atomic radii back when we talked about periodic trends, okay, I don't know if we actually discussed this, but what they do for the atomic radii is they measure the distance between the nucleus of the two atoms, and then they take half of that being the radius. So when we look at this, let's look at fluorine right here on our periodic table, and then chlorine, bromine, and iodine. Let's look at those four. As we're going down the halogens there, we would expect the atomic radius to get bigger, wouldn't we? Because that was our periodic trend. As we go down, we're getting bigger. Why? Because we're adding more electrons. We have more electrons. Obviously, fluorine, if it's neutral, only has 9 electrons. Iodine down there at the bottom has 53. So when we expect that there be more shells and have a bigger radius, absolutely. So let's look. Here's fluorine right there, 64 picometers, okay? Picometers, we talked about that. Down here is iodine, 138 picometers. So if we look, fluorine, then chlorine, then bromine, then iodine, they're all getting bigger, which is the periodic trend for the atomic radii. This slide I put on here, once again, you can see the 7 of the super 7, but I put this one on here because we'll talk a little bit about a polyatomic molecule. Now, is a polyatomic molecule different than a polyatomic ion? Are molecules different than ions? Absolutely, okay? If you say a polyatomic molecule, that would tell me that they are covalently bonded together. A polyatomic ion would tell me that they have gained or they have lost an electron somewhere, okay? So polyatomic ions, they could be negative. Most of them are negative, but some are positive. There's a few we deal with that are positive polyatomics. But we're looking right here at sulfur, okay? Here's a common way that sulfur bonds to itself, S8. Here's phosphorus, P4. Some ways that sulfur and phosphorus bond together as opposed to the super 7, the diatomics up here. Now, when we talk about some properties of the diatomics, and we can see this on our periodic table based on the color. I can see hydrogen's red. I can see nitrogen, oxygen, fluorine, chlorine. Those are all red. So that tells me that at 25 degrees Celsius, that those are gases. Okay? I look and I see bromine is blue. Well, that tells me that bromine is a liquid. All right? So at 25 degrees Celsius, which was somewhere right around room temperature, okay? 25 degrees Celsius, bromine is a reddish-brown liquid. Now, looking back here at iodide on the periodic table, its symbol is black. That tells me that it is a solid. So this is a lustrous, dark purple solid would be the iodine. So these don't necessarily have to be gases because two of them, the two on the bottom, bromine and iodine, are not gases at room temperature. A polyatomic ion. Okay, once again, when we broke that down, poly is many. So this is an ion that is made up of many atoms. So a polyatomic ion is also known as a molecular ion. A molecular ion because it is covalently bonded, but then it forms an ion. So there is sharing of electrons between the different atoms, and then there's also a transfer of electrons. As I look at a polyatomic ion right here, as I look here, I can see that I have 1, 2, 3 oxygens bonded with 1 nitrogen in the middle. Now, this is a double bond right here. So oxygen and nitrogen are sharing these 4 electrons, so that makes this oxygen happy. This oxygen right here has 6 of its own electrons, okay? And then there's this one red one. That one red electron is the one electron that has been gained by this particular polyatomic ion. Now, if you look right here, okay, both of these are black, okay? So this oxygen, it has 6 valence electrons all wrapped around itself, but then these two right here are both nitrogens. What this is, and you don't need to know this, you're not going to see this on a test or anything, but this is what we call a coordinate covalent bond. And that means that nitrogen is just nice enough to say, oxygen, I'm going to share 2 of my electrons with you. The nitrogen gets absolutely nothing from it. The oxygen gets a full outermost shell, doesn't it? Okay, by sharing those 2. So that's a coordinate covalent bond. Note that the one extra electron that is red in this color, okay, it is required to complete the octet. The resulting complex has a negative charge. That's why we put these brackets right here around it and put a -1 there, to know that that entire complex here has a -1 charge. Now, does it make sense? Sodium's an alkali metal, right? Sodium's an alkali metal. Does it make sense? We know that sodium wants to get rid of 1 electron, right? So does sodium, if we know that this nitrate over here, which is what we call this guy here, nitrate, if we know that it needs to gain 1 electron, doesn't it make sense a bonding partner to be sodium because it wants to lose 1? Or any other alkali metal, lithium, potassium, rubidium, any one of those would be good ones to bond with this nitrate here. So these are covalently bonded. They are sharing right here, okay? Sodium then comes and gives up this 1 electron right there. So that is ionic bonding. So when we see these polyatomic ions, we know that it has both types of bonding, that it accepts, okay, there is a transfer of electrons, and there's also the sharing of electrons. Now, this final slide here that we're going to talk about is 2 polyatomic ions bonded together. Now, as you can see here, I have, and I told you that we do have positive polyatomic ions. This is one of the most common ones. This is probably the most common positive polyatomic ion. So a polyatomic cation, it is the ammonium ion. Now, as you can see, these X's are the electrons donated by hydrogen. Notice that this guy right here, there's no X, is there? So this is missing an electron from the hydrogen, because nitrogen has its own 5 right here, 1, 2, 3, 4, 5. Nitrogen has its own 5. So nitrogen is sharing both of these electrons with hydrogen. Well, where did this hydrogen's electron go? Well, how about right over here? Okay, when we bond this together, we have oxygen and hydrogen. Hydrogen's happy here with its 2. This oxygen has 6 around it. The hydrogen 1 makes 7. Therefore, it's missing 1 valence electron to fill the shell. So it covalently bonds right here with the hydrogen, and then it accepts the electron from this hydrogen right there. So the charge, the plus charge and the minus charge go together, right? We're going to learn later on that when we're writing this, the name of this compound, it would be NH. We have 4 of them. And then OH. That would be how we would write that particular ionic compound. So since that's ionically bonded, could we call it a salt? Yeah. Yeah, we could. Okay. Any questions for me about diatomic molecules or polyatomic ions? Let me just show you one thing before we end it here. You'll get one of these later on. You'll get one of these later on. This is what I call PAL. See the big PAL. That's a polyatomic ion list. And this shows you how many polyatomics, and this is just one list that we compiled throughout the years. You'll get more than one of these lists, but it shows you that there's a lot of polyatomic ions. Okay, all of these on here. Most of the polyatomic ions end in either ATE or ITE. We talked about that NO3 1 minus. That is nitrate, the ATE ending. Okay. All right.